Welcome back to the Deep Dive. Today, we're looking into the story behind a name maybe not everyone knows, Ernst Ruska. And our mission, really, is to map out how his work with the electron microscope took a physics idea and turned it into this massive tool we now use to see, right down to the atomic level.
Yeah, it's a fascinating story, and it kind of starts with a bit of irony, actually. Ruska's family, they were all academics, right? His dad was a historian, his uncle an astronomer, but his first run-in with a light microscope wasn't exactly inspiring. It was punishment. He apparently saw this forbidden device as a kid while he was supposed to be sitting quietly.
Huh. So maybe that little bit of rebellion against the standard tool kind of pushed him towards engineering?
Could be. It certainly led him down that path. So jump forward to 1928. He's at the Technical High School in Berlin. And he wasn't dreaming of microscopes yet. His job was honestly pretty mundane sounding, shrinking the spot on a cathode ray oscillograph, for measuring electricity faster.
Okay, kind of try. But that led to the breakthrough.
Exactly. That was the catalyst. See, he was working with Hans Busch's theory from 1927. Busch had figured out mathematically that a short magnetic coil, it should work just like a glass lens, but for electrons.
Like focusing them?
Precisely. And Ruska actually proved it. In 1929, for a student project, no less, he got the first electron optical images recorded sharp magnified pictures of a tiny anode aperture, just 0.3 millimeters. But still, the proof was there.
Okay, so he's got an electron lens.
Yeah.
But one lens isn't really a microscope, is it? What came next?
Right, you need more stages. So April 1931, that's the key date. Ruska hooked up two magnetic coils, two lenses, one after the other, and that was the first real electron microscope principle in action. Now, the magnification was small, only about 14 times, 14.4x, I think, but it showed the whole concept worked.
Then things get, really mind-bending with the whole resolution idea, right? He finds out about Louis de Broglie's hypothesis.
Ah, yes, de Broglie. The idea that electrons aren't just particles, they act like waves too, and that realization must have been huge for Ruska.
Does it?
Because he understood, okay, the resolution of my microscope, how much detail I can see, it's going to be limited by the wavelength of these electron matter waves. And he did the math. Quick calculations showed him these electron wavelengths had to be like 5 orders of magnitude shorter than light waves.
5 orders?
Yeah.
So not just 5 times better than a light microscope, but like 100,000 times potentially.
Exactly. It meant the theoretical limit for resolution was just unbelievably small. So in 1932, he and Max Knoll, they actually published a prediction. They said, we think we can eventually get down to 2.2 angstroms resolution.
Which is atomic scale, basically. 1/10,000,000th of a meter. Wow. Did they actually achieve that, though?
Well, eventually. It took about 40 years for technology to catch up to that prediction. But to even get started down that road, they needed better engineering than just simple coils.
Right. You need serious power, serious focus for these electrons.
Absolutely. You're talking high voltages, like 75 kilovolts, to get the electrons moving fast enough. And you need to focus that beam intensely. That's where the pole-piece lens came in. Patented in 1932. It was ironclad, literally, and it squeezed the magnetic field down really tightly.
Making the focal length shorter.
Much shorter, just 3 millimeters for those 75 keV electrons. And that compression is what let him jump to 12,000 times magnification in his 1933 prototype instrument.
Okay, the science seems solid. The potential is huge. Why wasn't this immediately, an industrial product? Why the delay?
The usual suspect. Funding. It was just really tough to get people interested. They saw it as maybe a physics toy, a curiosity. The breakthrough for funding actually came from medicine. In 1936, there was this assessment by a Professor Seebeck. He basically said the impact this could have on disease research would be incalculable.
That must have turned some heads.
It did. That statement finally got Siemens on board. And Siemens delivered the first commercial, serially produced EM late in 1939. That led to those amazing early images people started seeing. The surface of a housefly's wing, bacteria, even tiny viruses like bacteriophages. There was even an early guest lab in 1940, though sadly it was destroyed later.
Let's jump ahead then post-war. Siemens comes out with the Elmoscope in 1954. They're tackling a new problem, right? Specimen damage from the beam's heat.
Yeah, the beam was basically cooking the sample. So the Elmoscope had this clever two-condenser lens system. The idea was to focus the beam onto a much smaller area, small region radiation, they called it, to try and minimize that heat damage.
Brilliant solution. Did it work?
It worked, but it immediately created a totally unexpected new problem. Became known as the carbon trap. See, because the sample itself was now cooler, any leftover hydrocarbon gases floating around in the vacuum chamber, well, they started condensing right onto the specimen, building up this opaque layer of carbon gunk.
Oh no. So you solve the heat problem, but now you can't see through the contamination. How did they fix that? Cooling caused it.
So they cooled more. It sounds counterintuitive, but the solution was actually quite practical, quite ingenious. They cooled the entire environment around the specimen using liquid air. That made the surroundings much colder than the sample itself. So now, those pesky hydrocarbons condensed on the cold walls instead of the sample.
Clever. Keep the junk away from the target.
Exactly. And that, combined with other big advances around the same time, like figuring out how to cut samples incredibly thin using fractured glass edges, ultramicrotomes, that really opened the floodgates for biological research.
So thinking about this whole journey, what's the big takeaway here?
Well, if you loop back to the start, the whole story of the electron microscope is this constant struggle with the very thing that makes it powerful, the electron itself. Its super short wavelength gives us that incredible resolution. I mean, seeing gold crystal layers just 1.4 angstroms apart, that's amazing, but the high energy you need for that short wavelength, it inevitably damages what you're looking at, especially delicate biological stuff.
Which leaves us with a really interesting thought, doesn't it? Something for you, the listener, to consider. If getting that atomic level view means blasting the sample with enough energy to potentially change it, maybe even damage it, how much of the image we finally see is the real thing and how much is, well, an artifact of the process? It's why today so much advanced imaging involves things like cryotechniques to freeze samples and heavy computing, averaging hundreds of noisy, damaged images just to get one clear picture. It's this endless quest, isn't it? Seeking clarity without causing destruction.